Okay. Hey guys. So this is Crimson Modder. I'm with my twin here, Shelter. Um, Laboratories. What he is going to be covering today is the MSP430. It's a microcontroller unit, and so we're going to be really going over the documentation. So without further ado, Shelter, go ahead and take over.
So this is the MSP430 F5529LP. It is a microcontroller unit evaluation board. We're reviewing documentation only today, and we will probably review documentation tomorrow as well. So our application is a data acquisition system. Don't know if I mentioned that. Um, so the MSP430 has a 12-bit analog to digital converter. Um, we are working with the MSP430 because it has an incredibly high sample rate, and we need an incredibly high sample rate in order to read high-speed data from an accelerometer. We've chosen a uniaxial accelerometer, model 3030B4 from Dytran. This is it right here. It is a 1032 axial mounting connector, and we have a 1032 magnetic plate to attach to a transmission. And we will be reading vibration data from a transmission, and we need it to go as high as 100,000 kilosamples per second, or sorry, 200,000 kilosamples per second, so we can read 100,000 kilohertz of frequency according to the Nyquist theorem. Uh, Uniaxial accelerometer is connected to the charge amp provided by Dytran, and then we will connect the charge amp to an analog to digital converter provided by the microcontroller unit. The MSP430 uses ADC12. The ADC 12-bit, which is a TI standard. We are working with micro SD data communication, so we can store the data, which is the data acquisition part of the data acquisition system. Uh, the micro SD will give us an easier method of interfacing, and it will also provide a low power alternative and allow us to carry the data acquisition system with the vehicle, as we can analyze while on the road, and then we will do off-board analysis using LabVIEW and MATLAB and pull the data off of it automatically and have it ran. In the future, we have an antenna system, and we can use that to transfer data remotely, but that is not a part of this project right now. So the first thing is to we will review the microcontroller units only. So the first thing we'll need to do is initialize the analog to digital converter, and the way the microcontroller unit works with the analog to digital converter is it uses an interrupt flag and interrupt vectors. So we'll need to set those up. And then we will need to initialize SPI communication. SPI communication is a standard communication protocol, and it is used widely, and it is especially used by the micro SD card. It is a 3 or 4 wire communication. We are using 4 wires. Uh, we'll get into that later, but essentially we'll need to transceive with the micro SD. First, we have to initialize SPI at the MSP430, and then we will need to initialize it at the micro SD. So the micro SD also has micro SD standards that we will have to follow in order to wake it up, reset it, and initialize it and prep it for data transfer. After we do that with the MSP430, and then we will be able to contact the micro SD. The micro SD is formatted in FAT32 intentionally. That makes it easy to communicate with, and it makes it easy to store data. So we will have to pull uh, bootstrap loader information from the micro SD sectors, and we can use that to find a free sector to start um, putting data from the ADC in FAT32 format to the micro SD. Some documentation here on the micro SD, sorry, the MSP430. I think the best place to start is probably the user guide for a quick review on the wiring. And it is right over here. They show the wiring or the pinout. So the analog in pinouts are all part of the ADC12, and we are also using, so that includes, that's all the pin 6.0s, including pin 7.0, 6.0, 6.1, 6.2, 6.3, 6.4, 5, and 6.6, and then 7.0. That's all part of the ADC12. Then we also have SPI, master out, master in, slave out, chip select, and we are using um, the clock. UCA 0 STE. This is the UCB 0 clock, specifically where you're using UCB 0 clock, and that will give us our SPI clock signal. Now we go to the API. So we are working with the ADC12, so specifically I can pull up the ADC12 for an introduction on it. Um, Without getting too deep into this, it tells you how to initialize it, and it tells you the different options you can select for it. Important right now is the voltage reference generator, um, and how to set that up. So we're using internal 2.5 volts, but eventually we will need a an external voltage reference so we can go over 2.5. And there is a limit on this, and I believe the limit is 5 volts. So we will have to limit that because the charge amp is capable of going up to 10 volts.
Yeah, and so just to note, if it does obviously go above its 5 volt capacity, it will basically fry. So be very careful about that.
Correct. There are other options you can select here. There's also, most importantly, for programming, especially, are the registers. Um, you have sample and hold times. You can tell it to uh, collect samples. The higher sample hold times value you have, the slower it is. We really want raw data so we can do a frequency analysis. So we do the slowest one or the lowest number. So we do the fastest cycle. So all of these are important to review, and we'll do that in the next one when I am better prepared to review this. But this is the first option for the ADC12. You have another option that this needs to be configured. This gives it timer sources and clock dividers. So essentially, you set up the ADC12 clock. Um, there is another one. This is where you can change the resolution for it. MEMX. This is the um, register that you call to pull the data from the ADC after it has captured the data. So this will give you your actual value. Interrupt enable. This is this is how you actually allow the ADC to interrupt the microcontroller unit. So you enable the interrupt, and then you call an interrupt flag, and when you call the interrupt flag, it will interrupt the system, and then it will go to the routine that you declare for it. So you have to declare a routine, which they did not state here. Part of the difficulty of programming with Texas Instruments' wonderful obfuscation of documentation. And then you have the interrupt vector. This is this is what you use with the interrupt flag in order to call it. So I think this is a good start. Um, Probably the next order of business is to actually show the program.
Yeah, so can you go over a little bit about the IDE that we're using, the text editor, and how you came to find that? Was it recommended?
So this is Code Composer. This is used specifically with Texas Instruments evaluation boards and microcontrollers. So not just the evaluation board, but it allows you to. It's Texas Instruments proprietary compiler. It's mainly in C. They do assembly and they do C++, but it's mainly ANSI C. The important thing about using this compared to anything else is it allows onboard debugging and register viewing. You can view the registers of your microcontroller unit. So maybe I'll just run it. Yeah, she's ready. I'll just run it and show you stuff that you can't do on a normal IDE. Um, okay, so this is what it looks like when you run a successful compilation. I won't say program yet. So you've got your registers here. It gives you your memory address and your values for each thing. Um, let's see. As I run the program, you'll see more registers pop up. But you have a registry map that you can actually look at. You can look at the whole sector table for the entire microcontroller unit. You can put data up here to watch. You can set breakpoints. This is why it's important to use Code Composer Studio. So in the program, and since we're reviewing the analog to digital converter right now, I will review just that. So we start with the main function, and you shut off the watchdog timer because I am not working with that right now. There's no reason to. Watchdog essentially, if you don't shut it off, it will reset the microcontroller unit if it times out. So you need to give it a constant signal, or you can just stop it. So we're configuring the ADC. We're using pin 1.1, which is the button, as an interrupt flag. And we will handle the interrupt by turning on a trigger. So, because we will constantly be pulling for that trigger value to be 1, and that's what will actually start the conversion. So we set the pin 1.1, which is the button, set the pull-up resistor for it. Pull-up resistor, you don't know, is essentially it tells the system that it's ready to read logic now. Um, Otherwise, it remains in an unknown state, so it gives it a known state. Then it knows what is high or low. Um, since we're pulling up on the resistor, I think we are setting it to low. Actually, that is exactly what we're doing. So it normally stays high. And when we set it to low, that's when it starts to read data and it goes, oh, I'm set to low, I'm reading 0. And then the next time we pull it high, it's going to read a 1. Otherwise, it doesn't read. Um, we trigger on the falling edge. That's just a trigger type. I don't really need to mess with that right now. So we just set it to falling edge. And then clear interrupt flags. This is important because if you don't clear it, then sometimes it doesn't clear. And then uh, if you have a interrupt that isn't being handled, it will spin continually and
Now,
it will not tell you sometimes.
quick note. So for some of these that we need to come back to, I think it would be wise to put a comment up above it and to do like a obviously a to do in all caps, and then the point at which we need to edit any of these triggers. So say for the falling edge, I think we should add another line between 38 and 37 for lines 38 and 37.
Wait, really? Wait,
Yes, and then this is just good convention. And then add a space. So go up
but
to.
hold on.
Hmm?
But the falling edge, what I'm saying is, well, we don't mess with that for this project.
Oh, okay. So, okay. Well, I guess as an aside, then for anything that we will be messing with for this project that needs it to do, make sure it's demarcated, or else we could kind of become unorganized. It's just good convention, and it'll help me out too. So
Got it. I don't
as
want
we're
to
going
mess
over
with
this,
my script too much, though. I got it organized very particularly.
that's fine.
You can probably tell I'm not a very good programmer. Anyway, but this is to do. This was added. This is for the micro SD card initializations, SPI initializations. We're not working with this right now. So this is just the ADC trigger setup. Um, this is the button 1.1 for the ADC trigger. That allows you to hit the button. We are pulling for that trigger. Pulling, that's POLL. Um, and we are waiting for the button to tell it when it is 1. And then further down here, let's go to the button interrupt flag. So when you hit the button, because we have configured it to be an interrupt vector, this is where we declare that vector. This is how you declare the vector. You use the hashtag progma vector equals port1 vector. The name doesn't really matter for the button. I'm not exactly sure about this stuff. So this is declaring the interrupt vector function. Set the trigger to 1. clear the interrupt flag, and then wake up the CPU. It is a low power microcontroller unit, so it always has the CPU off. Um, when we set the trigger to 1, we handle that. Let me go on up here. Eh, eh, I'm always lost. Hold on. Man, I'm lost. Here we go. When we set the trigger to 1, we start a function called start conversion and reset the trigger. Declare I. So start conversion function has a pre-requirement. We actually need to configure the ADC. That was done in a separate function. Here, this is where we actually configure the ADC. So in order to fully configure the ADC, we set the sample hold time and we turn the ADC on with ADC CTL0. That was in the documentation. ADC CTL1, we configure by telling it to use the sampling timer. ADC CTL2, we configure it by telling it to use the 12-bit resolution. The ADC12M CTL, that's the voltage reference. We tell it to enable channel 1 and reference VREF 2.5 or reference the internal 2.5 volt reference. We set the interrupt enable, so the ADC is allowed to interrupt the system. And then we set the, well, sorry, this is a archaic. This is the archaic voltage reference set because there was an issue with my microcontroller unit having mismatched versions. So this is just a redundant setting the 2.5 internal reference again in case there's an issue. Give it a slight delay so you can allow the internal voltage reference to settle. And then we are configured. This runs before this runs at startup. Then we run the start conversion function when the trigger is 1. ADC 12 CTL enable channel 1 and start conversion SC. This allows it to start the conversion, and that is taken over by the interrupt vector here. This is our interrupt vector. It is a switch command. So there are a few commands that you can do. When we call the interrupt vector, we are using case 6, which is the ADC12 mem0 interrupt. This is where mem0 is where it pulls the actual value. So we actually just add this to a sum and we average this a few times. I toggled the LED so I could see it blink. Clear the interrupt flag, set a trigger, and this one gives me a timestamp. So this is the timestamp gets wiped every time, but I'm using it in debug right now, so I don't really care. Essentially, this is important because I don't know why you would want to sample without a timestamp. So you actually have to set up the internal clock so you can pull the timestamp information. That is done up. Where did I have it done at? This is the clock setup. This is where you set the clock. This is used for collecting the timestamp data. Um, there are a few options. Again, you can review the documentation here, and we'll review that later in fuller detail as we continue through this project. But essentially, this is how you initialize the clock for how I'm using it. Continuous mode, clear the timer when you initialize it, and use the SM clock source, which is part of that wiring diagram. You can see what clock source you want to use. And back to the interrupt flag setup. So you get your timestamp, and then you break after you've cleared the interrupt flag. You break out of this. It runs out a few more times. Um, here, when the conversion is complete and we're done with the for loop, we divide the results, and I make that available by setting a breakpoint so you can read the data. And that does that for the ADC. So this is just a very simple analog to digital conversion. This is uh, the future for this is to set it up as comma delineated. Essentially, we want this to be output in comma delineated format in FAT32. So we'll need to build a table of ADC results and timestamp so we can pull the frequency information from that. But we run that. So when you start the script, it starts at a breakpoint. Whether you've set that or not, it'll start at a breakpoint. All right. So when we run, it will sit here. Oh, hang on, Twin. Actually, I can't run this script. All right. So that does it for setting up an ADC for a simple readout. And later we will review setting up SPI and getting a micro SD card prepped for bootloader information. And the goal for that is to properly read information from a micro SD card interfacing with the MSP430 through the debug interface, and from there we can uh, work on our next step, which is successfully uploading ADC results in CSV format and declaring that as a file.
Yes,
Um,
and this has been a pretty software heavy stream, and of course just going over documentation. So a lot of data to take in, but in the future we're also going to be showing the hardware as well as the software, and just how we set it up. So yeah,
includes this.
have a good day.